Okay, the last problem, it is pretty complex. It looks complex, but I think we can handle it. The first question is asking us to determine the height h. So this is the h they're talking about. Okay, keep in mind that this is going to go down and then go around the thing and then come off here. And when it comes off here, it's going to come off with a velocity of 4.0. Now, just keep in mind we're going to have to break that down into an x component and a y component. So we'll do that as well. But let's just start with here. I have set it up, again, like an LOL chart, is we have all of the potential gravity here, potential energy here, but no kinetic. And then it comes down and it goes around and does a bunch of stuff. But again, similar to that skate park activity, we're assuming no friction and all of the energy is combined. So when it exits here with a velocity of 4 meters per second, that's some information that we need and that we can use. Let's go ahead and start doing this. So as always, we can cancel our mass. The mass does not matter. And now we have g, which we can put in a 10 meters per second squared, times the h sub a, and that's what we're looking for. And over here, well, the only velocity that I have, I'm using the velocity at c. And then I'll go back and do some other things so you can see where I'm going with this. But I'm going to use the velocity at c because that's the only thing that I know right now. So I'm going to go ahead and square that. So on the left, I have 10 times h sub a, and on the right, I have 4 squared is 16, and half of that is 8. So if I divide by 10, I get that h sub a is 0.8 meters. All right, but let me go back. Remember I said I was going to use that c, but I was going to tell you what I'm doing. So come back to the diagram. And really what's going on is that 0.8 meters is only this part of it, above kind of that exit time, because we were assuming that was like the bottom, but it's not. There's more. And so this was 0.8 away from the C, but we still have this 0.5 meters here. So our total height, 0.8 meters plus 0.5 meters for a total of 1.3 meters. So our total height is 1.3 meters. All right, next question is a free body diagram. When it is at point B, where is point B? There is point B. Okay, when it's at point B, and again, we haven't talked about centripetal motion at all, but I think you know that the normal force should be coming out this way, and the gravity is going to come out this way. Those are the only forces, is the normal force and the gravitational force. On the test, I'm not going to have anything related to concepts we haven't studied. Question C, determine the magnitude of the velocity of the block when it is at point B. Well, once again, point B, notice the diagram. Point B is in line with point C. So if it is at 4 meters per second as point C, it is also 4 meters per second at point B. So that's the answer on part C. Okay, part E, we are going to have to go back and use a kinematic equation. Determine the maximum height above the ground attained by the block after it leaves the track. And remember I said we were probably going to have to do some components. So V sub y, and this is a 30 degree, right? Yes, it's a 30-degree angle. So V sub y is 4 times sine of 30. And 4 times the sine of 30 is 2 meters per second. So going in the y direction, we have a velocity of 2 meters per second. And I needed that one because this is asking for the maximum height above the ground. So I'm using this, and I'm using a delta y because we're talking about height. So its final velocity when it gets to that max height, that's the top of the parabola, that's 0. Now its initial velocity in the y direction was 2 meters per second squared. A is 10, and let's use a negative 10 because gravity is working against us in this case. And then we, of course, have our delta y. This is a 4. We're going to subtract it and get a negative 4. We have a negative 20 over here, and we are solving for delta y. So delta y is equal to 4 over 20, which is 0.2. Now, once again, that's not our total. We have to look back at the picture, because what we're saying is it's going to leave here and it's going to go up 0.2 meters
above here, and then it's going to come back down, right? Well, that's 0.2 meters above that, but that point was 0.5 meters above the entire thing. So we have to add on that initial 0.5 meters. And so our answer is 0.7 meters is the total maximum height that it achieves. All right, last question is part F. And part F, they are adding in friction to this situation. And they're saying, okay, if we are adding in friction, it is found that if the block is to reach point C with a speed of 4 meters per second, the height h must be 2 meters. So they're saying if we have friction, we need to start a lot higher than this. This 1.3, which is what we had, 1.3, is not high enough. We need to go up and start at 2 so it has enough energy to go off at the speed that we want it to go. Determine the work done by the frictional force. Well, the work is going to be how much work has left the system, how much energy has left the system. And the way we find out that change in energy is we take the new energy minus the old energy, and that's going to be the difference. Well, that is going to be mgh new minus mgh old. And maybe instead of new, I can call that final. Instead of old, I can call that initial. So that means that the work is, this is just change in energy, okay? Because the change in energy is how much we lost. So if that's how much we lost, all we have to do now is we just have to start plugging in some information. So our mass is a 0.1 kilogram. Our gravity is 10 meters per second squared. And our height, well, we're talking about it, we need it to be 2 meters per second, just 2 meters. And originally we had it as 1.3 meters. I can do this math in my head even, or my calculator, because that comes out to be 1. 2 minus 0.3 is 0.7. And that is energy that was lost in the system. So with our LOL chart, we would say that we lost 0.7 joules. And so sometimes we call that negative because it was lost. But if we just write in the word lost, that's pretty good too.